Hi, thanks for having me. I've been here last year on a talk on polars, and I think it was more introductory that time. Went more into the details of what we do under the hood. Um, and I am allowed to come back this year as a keynote, so I'm really honored. Um, my name is Ritchie Vink. I'm the author of polars. I started the project 4 years ago. Originally, I have a background in machine learning and software development, and if we even go further back, I have a background in civil engineering, but it's not really useful to this. Um, and um, since a year or 8 months, I'm also co-founder of a company named Polars as well. Um, Very original name. And today I want to give a short introduction to Polars. um, but I'm not going into what we do under the hood. Have been plenty of talks of that of mine, which I want to share. But today I want to look a bit about to what we have done the last couple of months and what we are going to do as a company. And I hope I have time for a demo. Yeah. So as an introduction, data frames, how they were used on a single machine. I think everybody thinks about pandas, right? If we think about data frames on a single machine, we think about pandas, or we think about R, dplyr, maybe data table. But mostly pandas was the predominant in people's minds. And the way we used to think about data frames was always in a materialized form. We were always thinking about the data in a data frame. And you could think of that as a list of series, where the series are the columns, and they have data. And if you do an operation, you will immediately get another data frame as a result, right? This is familiar, I think. But the goal of Polars was to, and is to, change this concept of what data frames should be and what data frames are. And there should be some steps in the middle. So Polars likes to think of data frames, we call it a lazy frame, where it's a column it's a DAG of operations. Does everybody know what a DAG is? Raise your hands. Right, right. For those who don't, it's if you write an operation, you just keep track of that operation, and you do the following operation, and you keep, for instance, a tree. You keep a tree of operations, or DAG is a directed acyclic graph, but you keep a data structure which keeps track of which operations you want to do, but you don't do them yet. It's lazy. So if you do an operation, you will get another lazy frame, another DAG, and we don't do anything. Except when you ask for materialization. With materialization, we mean producing the result, producing the data. At that time, we go through an optimizer. This is very similar to what a database does. When you send a query to a database, or when you write, for instance, a C program or C++ program, the code will never be executed as you have written it. It would be extremely wasteful to just follow the programmer. Because programmers think in high levels, think in high abstractions, but an optimizer will take that code and will see, hey, how can we do this smarter? Which things can we elide? Which things were not necessary? Which things can we do better? And as it turns out, with data, we often work with millions of rows, right? It's pretty common. So there's a lot of time to keep thinking of what makes sense and what doesn't. If we don't need all the columns, please don't load all the columns. If we do filters as soon as possible, we drop rows earlier. We don't have to use those rows in a join. So this optimization part is super important. And this was totally missing in single node data frames. PySpark did it for big data because you have to, otherwise it's impossible. But for single node data frames, this was totally ignored. So we go through an optimizer, and then we go to an engine. And also the engine part was not getting a lot of love originally on a single node. The engine part was always single-threaded. It used NumPy often, or it used an already existing abstraction, which is really good. NumPy is really good for what it was designed. It's really good for numerical computing. If we're talking about relational computing, it's not good. It's not good at all. You don't have missing data. You don't have strings. You don't have nested data. And if you want those, you would need Python objects, which would make everything slow. So we designed an engine from scratch with parallelism in mind. We designed our own data structures. And this engine, we actually have 2 engines, and there are 3 engines coming, 4 maybe. But it's all abstract. It's abstracted away for the user. As a user, you just collect your data, and we will figure out, together with the optimizer, how to run this most effectively. So that's the thing I want you to remember. The engine is really important, and it's multi-threaded, and it is fast. And after that, you will get a materialization. You will get the result as a data frame. And then rinse and repeat, right? If you do another operations, you will go back into lazy frame land. And but the thing is, you should think of a data frame as an end result, and that is not as an intermediate step. So to summarize, I go very quick now because I don't want to talk about how it works on the hood, but polars can be it can be up to, I would say mostly ranging from 2 to 100 times faster than pandas. And this is because of a couple of things. One, polars takes database research into the Python data frame scope. So we don't ignore what all the database people have been doing. There's been a lot of fantastic research for decades. And that research was not really used in data frame, in single node data frames. It was used in PySpark, but it wasn't used in single node data frames. And we brought that into the single node data frame land. So we come with lazy evaluation, query optimization, which can give you speed ups. Generally, if you write a query which is perfect, which we cannot optimize, it will not have any speed up. But most of the time, we will find speed ups, and they can be super significant. It can be even more than 20x, but I would say most commonly it's that range. And the query optimizer can also do optimizations you cannot do as a user. For instance, you cannot push filters into a reader. You cannot push filters into S3 select. So you can also filter on AWS side, that kind of stuff. That's stuff we can do, but you cannot do as a user. We minimalize materializations. So materializations is producing data as an intermediate structure. And we use copy and write. We are slice aware in operations. That means that if we do a sort, but you only need the first 100 rows, we make sure we do a top K, for instance. So we don't have to first materialize a whole sort and just take the first 100 rows, which would be wasteful. The data types are constructed to amortize access and allocation cost. Have you seen the talk yesterday of David Hewitt on PyO3? That goes into that. It's written in Rust, so we have full control over memory, over threading, over critical paths. And if you write a data-heavy library, it's important to have control over memory. It's important to understand when do you do allocations, how do you access it, cache efficient, etc. That's why you don't see any databases written in Python. And it's designed for effective parallelism, and we have written all the I/O readers that we think are important from scratch. So we have written actually Parquet from scratch, we've written CSV from scratch, we've written JSON readers from scratch. We fully control the stuff that's important for performance. And we ship with 0 required dependencies. Everything is in the Polars binary. So as a result, Polars is one of the fastest open source query engines for a single node. So here we see results. So it's from left is Polars, DuckDB, Pandas, Dask, and PySpark. And Polars is what I think we're fastest in 4 out of 7. And Polars and DuckDB are one of the fastest open source query engines on a single node. And you can see the difference. This is on linear scale, but it really matters. The thing is, also, you don't have to tune. You just run the query, and it will run fast always. This is different from some other tools where you need to set cluster or chunk sizes, all kinds of hyperparameters to produce better results. We think the optimizer should determine this. as a user, you should just write your query semantically. So yeah, we have very good performance. That's the gist of it. Oh yeah, one note. Here, Dask and Pandas have actually run with hand-optimized queries. So they have some optimizations because they don't have an optimizer, so we're sort of lenient towards them. The PySpark, DuckDB, and Polars have to do the optimizations themselves. Yeah. So if you want to learn more about why we're fast and how we do that, I've given a few keynotes on this, so make a picture if you want to see them. And we talk a bit about the different engines we have, how we do parallelism, how we do query planning, etc. Yeah. But today I don't want to go into this again because, yeah, I also want to share some new things. So we started a company 8 months ago, but it took a few months to get started. I think we're now 6 months on a roll, and I want to look a bit about stuff that has happened since then, and also some things later on to look forward. But let's first look back. There's happened a lot with regard to integrations and adoption. Polars just hit the 5.5 million downloads a month this day, and this is very close to Dask, and I'm super proud of this. I mean, it's in 4 years now. Yeah, that we even come close to libraries which have been in existence for 10 or 12 years is amazing to me. And we see that in integrations. We see Polars being adopted by large libraries and people seeing the trust in using Polars and having the benefits of Polars. And we have been looking in core kernels. So there are, I'm going to go into this a little bit later, and we have done some optimizations, and I want to point out one. And I want to talk a bit about data representation. We've done a large refactor, and I also want to point out this one. So the first one is a lot of open source adoption. And there are big names here. Hugging Face, scikit-learn, those names are big, right? What we see is those libraries now, we see a lot of libraries now support Pandas and Polars. They say, okay, it's not, the time has changed. Users don't only want Pandas output. There's not a monopoly anymore. We want to choose. We want to be able to stay in our Polars pipeline. And libraries are adopting that. Another huge benefit from adoption is Arrow. We speak in the Arrow memory format. So our memory is allocated conforming the Arrow spec. So we can move out of Arrow 0 copy. And that means we can integrate with anything that speaks Arrow 0 copy. And we also see libraries going for Polars only. And they do that for a couple of reasons. One, for the performance and parallelism. Another one is the expressions. So an example of this is Great Tables, who just took the Polars expression and used that to being able to express their data querying in their API and just lift on the expressiveness of Polars expression and use that to make their API also richer. And we see a lot happening in plugins. So Polars plugins, if you do parallelism, you don't want to write Python functions. Because if you write a Python function, you're GIL bound. And even though you use NumPy under the hood, and after that you drop the GIL, going through Python means there is contention. Because if every thread uses a Python function, it first needs to hold the GIL before it can execute that function, and then that function needs to release the GIL, and then the other function can go. But you have contention. All the threads want to have the GIL at a point. So what we don't want to happen is users writing Python functions. And we came up with a thing called Polars plugins, and with that you get the best of a lot, because Polars plugins run on the Polars engine, and you get parallelism, you get every benefits of the Polars engine. They will also, the optimizer knows how to deal with them, so you also get optimizations like caching of expressions that are duplicate, etc. But you can write an expression in Rust, compile it, and expose it in Python and use that in your Python interface. So if you do something that's more exotic, like, I don't know, computing pods in, I don't know, something more exotic, you can just take a crate from Rust crates.io, which is sort of the PyPy of Rust, compile it and use it into the Polars engine. And you will get Rust speed, parallelism, optimizations, all for free. And it's actually quite easy to get started. So you also learn some Rust. So there's 4 benefits. Yeah, well, this is what I said. As I said, we are a query engine, and a query engine, a vectorized query engine, always needs to have a balance between how much will you precompile and how much will you do vectorized. So a vectorized operation, let's say if you compile a C program, everything can be run compiled in line. So if I do A plus B plus C, it can be done per row immediately. But if you do it vectorized, you will first do A plus B on a column, and then times C on another column, right? There are materializations in between. But you could also compile a kernel that folds these 3 operations, right? You could also compile A times A plus B times C in one kernel. But users will always do stuff you cannot precompile, right? Otherwise, you would need to precompile everything. So that's sort of the balance a vectorized query engine needs to take. How much will we precompile and how much will we run vectorized? And if you precompile, you will get maximum performance. There is nothing faster than that. You can do SIMD, you can do everything, but you don't want to precompile more. You cannot precompile anything. So there's a balance with how much do you precompile and how much do you keep as vectorized operations. Well, and here is an example of an operation, a core kernel. We thought this is so important that we need to precompile it, and this is the filter. And in the filter, we wanted to have maximum performance and put every inch of every optimization we want to hit, because filters are super important in data in query engines, right? You filter data all the time, so it's worth taking the effort to use special hardware acceleration. And hardware acceleration can be SIMDs. SIMD are special registers, which can, for instance, work on multiple integers in the same amount of CPU cycles as normal registers can. Or it can also be special intrinsics that shuffle some bits around. So you just have special operations that are specific to a certain hardware architecture. Yeah, so here's what we did. I want to look a bit about does anybody understand this NumPy chart? What we're doing is we take a Boolean filter from a row, and if we select null, we select 0 rows from the Boolean filters. Every Boolean value in that mask is false, and if we're here, every Boolean value of that mask is true, right? But what you see is that when we get more and more randomness, so here it's 50%, right? 50% of the Boolean values are true, 50% are false. The point is, it's not really predictable what it is. So what will happen is that the CPU will mispredict if it's true or false. And does anybody know about branch prediction? Yeah. This is what happens. What actually happens is that CPU does, if you write an if-else in C, then the CPU will choose one of those branches and pre-compute them, or do some pre-computing work. But if it chose the wrong branch, it has done that work in vain, because we don't take that branch, and it has to flush its pipelines, and this is very expensive. And as you see, so when things are predictable, NumPy is really fast, but the more randomness we get, the slower NumPy gets. This was our old line. I'm not going to explain it now. But this is our new line. This is what Polars does. It's completely branchless. That means that the CPU will never mispredict. That means it's always hitting the exact same performance, and the performance is also, the difference is huge, of course. But this is special hardware acceleration, but because of the importance of a filter, we think it's worth it. Yeah. Another one, an example is, I wanted to show this, that there is still a lot left on the table on single-threaded pandas performance as well. This is a rolling median, which we improved. And here you see the rolling median performance of polars versus pandas with a certain window size. So we don't only get speed from parallelization, but also from better algorithms or just better writing code with regard to cache efficiency. And this is all algorithmic, by the way. As you see, if we increase the window size, we now grow logarithmically, I think, where pandas also grows logarithmically, but with a different slope. And initially, we grew linearly, which was not bad, which was not good. So we fixed that. Another optimization we added in the optimizer. I'm really happy about this one. This is full scan common subplan elimination. So this is a query from the TPCH benchmark. The TPCH benchmark is a common benchmark used for databases. This is query 2. And in that query, there is a point where you join with itself. So you have a plan, and then you join with itself. But if you naively run that plan, you will run these nodes duplicates, right? So you will do the same query twice. So what we're now able to find those common subplans, and we can cache them, and this saves a lot of time. Really happy about this. Another thing we added is an async runtime. We're actually getting even more performance than we had initially. We're still tuning this. So an async runtime helps us, when we're going to S3, we want to get maximum downloading performance, because at that point, if you write a query and you get data from the cloud, most time it will be in the downloading. So it's super important that we only download the parts we need, but it's also super important that we max out concurrency. And there's sort of a battle with the threads we want to use with compute and the threads we want to use for concurrency. So the concurrent threads we want them to be able to properly use async I/O. That means that a single thread could do multiple things at a time, and put some stuff to hold and look at some other download if it's finished. It just shows that we had a lot of performance improvement. These are the new Polars streaming, Polars default engine, and we compared it to the previous Polars version where we didn't do this properly yet. I think it's a 10x, and we're faster than Pyaro on this one as well. We're still tuning this, but yeah, we added it. This is an important one. Here is where I want to go. We had a huge refactor for our string representation. Does everybody, I think strings are a hot topic in data frames lately, right? Everybody heard about pandas going to arrow strings, right? Or I assume so. Who heard about this? Let's put it like that. Right. Yeah. So we actually moved away from those strings. So we were not happy with it. They were presented as superstrings and they solve all problems. No, they come with new problems. It's all a trade-off. There are no superstrings. Strings are hard. Binary data is hard. It all comes with trade-offs. And we want to make the case that the trade-offs of the default arrow string are not worth it. And I'm going to explain a bit why. If we have a column with some data, ABBA, The Velvet Underground, Toots and the Maytals, my favorite bands, the way they are stored in arrow strings is you take the string, you concatenate everything in a long buffer, and then you keep offsets in that buffer. And then if you want to take ABBA, you take 0 till 4, and you've got ABBA. And if you want to take the Velvet Underground, you take 4 to 26. Right? Is that clear? Right. And this string representation is good because it's really cache friendly. If I want to iterate this, I just reverse linearly through the buffer. What I want to say about cache efficiency, if you go linearly, it's good. If you hop around, it's bad. There's only 8 bytes of overhead per string, which is good. It's not much. What's bad, or a downside, is it's hard to predict allocation size up front because everything needs to be in a single buffer. What if you append another string at the end? Then you need to reallocate a new buffer and copy all the strings. This can get expensive. If you have this on a 6 million string row and just at the end you hit this limit, you need to copy all the strings to a new buffer. You will double memory temporarily, which, yeah, it's hard to predict. But the pathological case here is that strings are not always short. So there are people who have whole web pages in their string columns. Now, what if you need to do a filter on this one, or a gather, and you need to create a new string buffer from this one, and you want to copy, let's say ABBA was not ABBA, but a large HTML web page, the string would be large, right? If I need to copy the string to a new buffer, I need to copy the whole string. So the gather operation, the filter operation, a gather is a take by index. It is linear complexity with the string size. And this can bring your query to a halt if you have large strings. It can get super expensive. So we made the switch to Umbra-style strings. Umbra-style strings are different in that you will have 2 buffers. One buffer will consist of 16 bytes, with 4 bytes representing the length of the string, 4 bytes representing the prefix of the string. So if the string starts with, if it's Aerosmith, the first 4 bytes you put in here. And if the string fits in those 16 bytes, you will just put the whole, or in 12 bytes, sorry, 16 minus the length. If the string fits in there, you will just put the whole string in here, and you're done. So the string is inlined. It's in those 16 bytes. If the string is longer than 12 bytes, you will still put the length in there. You will still put the prefix in there. But then you keep an offset of a buffer and an offset in that buffer. So you can have multiple buffers. And you can say, OK, this points to this buffer. And it starts at 22. That's where I need to search. And I know the length, so I can retrieve the string, right? The benefit of this is for long strings, I don't need to know my allocation size because I can have multiple buffers. And if my buffer is full, I can just allocate a new one, which is good. The second, if I need to gather or filter, I don't have to touch the strings in these buffers at all. I can just take the views. And maybe I need to update them, need to update the buffer indexes. But I don't have to copy the strings. The filter operation is now constant. So it's still cache friendly. Allocations can be sharded. As I said, you don't have to allocate a new buffer or not allocate the whole buffer. Actually, this inline of the length and the prefix allows for very cool optimizations. You can do a lot of fast comparisons, cheap hashes. You don't have to. You can have a dirty hash which doesn't have to take another cache hit to get to the string. You have a little bit more overhead per string. It can be it can be better or worse, but it's acceptable. And the downside is if we do a filter or a gather, we might need to do a garbage collection pass. But after all, it's still worth it. If we look at some gather filter benchmarks, you see the difference. And actually, we could have, because one is complex, the complexity of the new string is constant, the complexity of the old string is linear. So we could make these benchmarks as extreme as we wanted, right? So the point is, constant complexity is way better than linear complexity. So, I mean, if your string is 500 bytes, you don't even see the difference anymore. It's going from constant to 500. So it's a 500 times difference. Yes, so this was a huge refactor, but it gave a lot of performance benefits. And don't believe in superstrings. Every string has a benefit and a downside. Oh yeah, so that was sort of some things of what we've done. We've done a lot, but these are some of the things I wanted to highlight. And now I want to talk a bit about what's coming. And I got super exciting news, where which was just shared yesterday. Polars and NVIDIA will work together on making GPU accelerated data frames. We will enrich our default engine with GPU acceleration. NVIDIA engineers will help implement this. And yeah, I think for data sets that fit into GPUs in a certain data set size, this will allow you to have even greater performances, right? The benefit is you will still benefit the Polars optimizer. The better we make the optimizer, the better the GPU engine will be as well. So it's better than GPU. We already have GPU acceleration today on QDF. What we don't have there is an optimizer, which is important, an optimizer. We can even beat QDF on TPCH on a lot of points because we do optimization and they don't. But now we cannot beat them on the CPU anymore, of course. So this is what's coming. Really excited about that. It will be hybrid. So for the user, you just write a lazy frame and you write collect GPU is true. And we will figure out which operation fit best on the GPU. Is it worth it? We can even do a data race. We could even start on the GPU and the CPU, and whomever finishes first will get the result. So there's only win-win if maximum performance is what you need. Yeah, so super happy about this. And another thing we want to do is building Polars on big data. What we want is having the Polars API on every data set size. And currently, I think we're very good on a single node. We want to be even better. We want to be able to process any data set size that fits on your disk. And we can do this sometimes, but not always. And actually, we need to solve a few problems. And the problems we need to solve are similar on Polars for the distributed engine as for the streaming engine. And before we make the two engines, we want to take a step back and always think we need a proper foundation for this, right? You don't gonna build a palace without a foundation. First, you need to think of what's my pile length, what the load will be. So there are a few problems we want to solve, and that is the problem of data access. So the Polars API is influenced by SQL and NumPy, and it's sort of a love baby between the two, because in the Polars API you can access a column at any time. You can access a column in a group by or in a select, but at any point you can access the whole column and select the first value, the maximum value. Whenever you want, you can access that whole column. So that's visualized like this, right? In the API and in the Polars default engine, at any point in time you can access any column from beginning to end, and also any column, so that's why we have the horizontal arrow. If you talk about a distributed engine or streaming engine will not get the whole data set size in scope, right? That makes sense, right? Because we cannot. So such an engine will only have a small batch where it can access its data. It can access horizontally the whole batch, and within that batch it can access the batch art, but not more. And a typical SQL engine can only access a row. In SQL, you cannot say, give me the maximum of this thing without writing a subquery. So that's also what we see here. If we, for instance, we have a table orders and we write a filter in Polars, we can write a filter where we say, okay, the order date equals the order date, but we filter where the agent code equals A0/4, and we take the maximum of that. And we can write that just in the API immediately. And we could do this, write this even in a join, or we can write this everywhere. Polars can access the data everywhere. In SQL, you cannot do that. In SQL, you need to write a subquery. So you see that in red. And this actually breaks up this. In this query, it's rather easy, but when you get more and more complicated query, finding the SQL equivalent of that will become harder, right? You will need more subqueries, and you need to think of, the programmer needs to think, how am I going to decouple these things? And in Polars, you don't have to. You can, the API is rich enough to let you access the data at any point in time. And I think that's worth it. I think it's, for a user, it makes sense to not be constrained by the limits of the engine, right? It's something that we need to solve. So here's another one where we can do an aggregation where you take the maximum and then you do you have nested aggregations. Nested aggregations are also not possible without doing two data passes. So this is not really, most SQL engines don't support this. Nested aggregations. Because this is easy when you have full data access. If you do a streaming engine, you need two passes over the data. So is the DSL too powerful? Because we have NumPy with full access to arrays, but in SQL you only have tuple access, relational access. I say it's not too powerful. I think that's how we think about data frames and how we want to think about them. But we need to solve a problem to make this full data access working agnostically. And a thing about this is, we see this in programming all the time. We have high-level abstractions in which we can do stuff where the lower level doesn't know about. There is no dot product in assembly, right? So we need different abstractions. On the most high-level abstraction, you have the syntax where you write the dot product. And you might go an abstraction deeper where you say the dot product is this, the magnitude of A times the magnitude of B cosinus theta. And on that mathematical level, you can do optimizations. If you find that theta is 0, you can remove the whole dot product and replace it with a literal 0, because you can prove that on a mathematical level, right? You can imagine that if you're doing optimizations in this abstraction, you can prove, you can use mathematics to do this optimization. This represents the same dot product. It's way longer. I just took a snippet of it. On this level, it's way harder to do the same optimization, right? It's way harder to recognize that we multiply times 0 here, for instance. But on this level, you can do optimizations on register level. You can see, hey, the register, this register is cheaper than that other operation. Maybe we can swap those. So every, sorry. So every abstraction has got different optimization levels and also different opportunities for an optimizer. And this happens in programming or in compilers all the time. You have different representations and some fit better for a problem. And this is what we will do in Polars as well. So we have on a logical level, we have a Polars query plan. The most top level is the Polars DSL, the domain-specific language, how you write your query. After that, we go into a full access intermediate representation. And in this representation, we will have metadata resolved. We will have schemas resolved. The names are resolved. So we know which column you select. You know the data types. We might know what the cardinality is of a column. We might know what the maximum value is of this column. And this information can be used to do query optimization. And this level is enough for us to go into the physical default engine. So the default engine can actually work with accessing all data. That engine knows how to deal with those operations. So, and the CUDA engine, the NVIDIA guys will build, also know how this works and how they can deal with full data access. So if you run Polars on a single node and you don't need streaming, this is enough, and you can already go into those engines. But we want to add another IR. We want to add a partial access IR. And expressions here that access full data needs to be translated to maybe just table operations, where you say, I'm taking this table, I do some operations, and then I cache it or I join it back with the original table. I first do the pass for the intermediate state, and then I will join it back. So it will be a limited IR. It will be a set of limited operations which allow us to run actually any Polars data query on all engines eventually. And after that, we will go into a physical planner and we can determine if we need the distributed engine or the streaming engine. Yeah, that's the foundation we are going to work on. We're working on this part. This is mostly finished. We need to have more metadata resolved. Schema resolved names is finished. The default engine and the CUDA engine we're working on. But we're excited about going into the deeper levels as well. And then I want to go to the demo. I think I have till half or 10 of them. Yeah. Okay. Cool. So I explained a little bit about the plugins, and I want to do a short demonstration about this. They have native integration, and you can build first-class citizens. So you can write a plugin, you can write something that becomes a Polars expression and feels like a Polars expression. And we're going to make a pig-Latin converter. Does anybody know what pig-Latin is? Yeah. I'm going to explain it. So if we have pig-Latin, what we do, we take a word, and if you have pig, we remove the first letter, so you get ig. You add the first letter to the end, and you add I to it. Ooh. Yes. So what would we, give me a word. Polars. Polars. So now what? Olars? Pi. Does everybody know what pig-Latin is? Yeah. We can make that, right? Cool. So I'm going to start with importing Polars, and I'm going to read a data set. This is a data set with 6 million rows, and I'm going to take the comments out, and I'm going to split them just to get a big data set full of columns. So what we have here is a data frame with 5 million rows and 16 columns. And it's 80 million string elements. And if we would write a pig-Latin converter, we could, the naive thing would be writing this in Python, right? So you could write it like this, a pig-Latinify, which takes a value string. If the length is 0, we return the value. And otherwise, we slice the first character off. We add the first value, and we add I. Does that seem correct? And in Polars, you can actually select all columns by a regex. So we select the comment names by regex, and then this expression will expand to all the columns, and we run this expression on all the columns. And I want to show this a little bit with, sorry. How do I remove this? I want to show this a bit with CPU threads and with hardware, so you can see what happens. If we would run this, we would expect a lot of GIL contention, and we also see a lot of memory increasement. I believe that's because there's some stacking with the lambda calling. But you see that even though Polars is parallel, you don't see any parallelization because of we are GIL contended, right? And it's also really slow because we need to allocate the string every time. This going through the allocator also adds a lot of contention because allocators need to also need to do some locking to keep everything. And in any case, it took 22 seconds, which is not great. We can do better. We could also use an expression to make this, to write this. So a Polish expression you could write is, you could take the string and you slice the first character off, and you take the remainder, and then you add the first value, so the slice from 0 to 1, and you add I, right? That's something we can do, and then we have a Polish expression of the same thing. If you would run that, it's finished. If you look at the parallelization, you see immediately a peak and a small memory bump. It took 870 milliseconds. But we can do better. We want the fastest pig-Latinify thing we can bake. So so the Polish expression still needs to vectorize, right? We still need to do the slice, and then we need to add that part, and we need to add the I. It's not inlined. We can inline it. So what we can write is a Polish expression. And there is some boilerplate. It's you create some. This is Rust. Can I zoom in? That's hard. Control plus. Nope.
No, it's Windows. It's not Mac.
Sorry? No, one at a time.
Mac, Windows. Sorry.
No, Linux. But this is. Ah, wow, that's cool. Wow. So yeah, we can create some quarks where this is some boilerplate where we can say this, we can deserialize this. This is some Rust code that actually does the value, takes the value, takes capitalized, takes an output buffer where we write to, and then we write a. This is the Rust code that does the Python code. You'll have to believe me that this is correct Rust that does the right thing. What you only need to do to make an expression is you create a pig-Latinify and you tag that with a Polish expression and you define the output. The output type can also be a function, but here it's a string. We define some inputs and some keyword arguments, and we return a series. And then we apply this pig-Latinify string over the buffer. How do I enter? How do I exit? Oh, view, exit. Right. On the Python side, we can import this. Let me go in again. Enter presentation mode. We can import polars. We can import some boilerplate to get the shared library. What we will do, we will link the shared library into the polars, the default polars engine at runtime. So you will register a, you will compile this library. You can push it to PyPy, for instance, as your own plugin library, and then you can import it in your polars extension library, for instance. So here we create a expression namespace called pig under a language class, and we add the pig-Latinify function. And again, this is some boilerplate, and this is all we need to do. And now I want to exit this again. View, exit presentation mode. Well, let's leave this on. And no. Let's run this one as well. So again, let's get some hardware here. So what we can do, here we have it. We take all columns, we say .pig.pig-Latinify, and now we run our own expression. And it's done. Voila. It's 3 times faster than the expression variant. And again, you get maximum parallelization and even less memory because we don't have to need to vectorize. So that we don't have to collect 3 strings, string columns. So yeah, this is sort of what I wanted to show on the. I could show a little bit more. What do you want? Do you want to go for the questions or do you want to? Come on. More? Okay, I got another example where we do some, where we show a bit about the streaming engine. That's the last one though. This is an example of how we can process more data than fit into memory in polars. We can do that with the streaming engine because it will automatically batch and has join algorithms, has group algorithms that understand how to deal with batches and how to do this properly in parallel. So here we load a 60 million data frame. If we count that, it consists of 59, yes, as I said, 60 million, 59 million rows. If we collect that, we would see that if we materialize this, it's fully parallel as again, but we see it barely fits in memory, right? I could fit one table, but that's it, right? So collecting is not what we want because collecting takes, if we collect this 4 times, it would not fit into memory. That's what I mean. So here we're going to concat the table 4 times. So we get 240 million rows. It doesn't fit into memory. And here we do a query from the TPCH query. It's a query that does a group by and does some aggregations, and then we compute the result in a streaming fashion. And if we look at the memory capacity and the CPU bandwidth of this, it actually almost takes no memory because we write the streaming engine in a way that is able to keep memory low, and it's finished. But you can actually reduce memory pressure a lot by using the streaming engine. It's actually, if something doesn't fit into memory, we can even sync to disk and do things smart. So, for instance, if you do a sort of a whole data table, you cannot be smart with, or you cannot be you need to do it with full passes, and you don't come. The output will not be smaller than the input if you sort the full table. But we are able to write to disk in a smart way to be able to finish this in a sensible time still. Yeah, and I want to go to questions now. This is sort of what I wanted to show.
Thank you so much.
Thank you.
Yeah, 1 second. We do have a question in Discord, so it just opens 1 second. Okay, how will the support of great modern CPU, GPU features affect the use of polars on old hardware?
How will
the support of great modern CPU, GPU features affect the use of polars of old hardware?
modern CPU, GPU features affect on old hardware? If your old hardware doesn't support GPU, we will run on the CPU, which will run on the CPU, which is fine. We have a compilation of polars, LTS CPU. If you have very old CPUs, with very conservative flags, you can install that. So if you have a very old CPU, yeah, we can support that. If you don't have a GPU, you will not get GPU acceleration, but I think that makes sense, right?
Is caching working the same way in polars as in PySpark?
Is caching working the same way in polars as in PySpark? Caching in what sense?
Data frame.
I think PySpark is. I know PySpark is distributed and it needs to have different caching strategies. It needs to shard the data. PySpark is written for distributed workloads alone, and it will have some design decisions that are not optimal for a single machine. That's why Polars beats PySpark on a single machine. And 1, because of design decisions. 2, because of where it's in what it's implemented. Polars is implemented in a columnar vectorized query engine. PySpark is written in Spark. It's on the GVM. Databricks itself has written the Photon engine, which is a C++ engine, which is columnar because of the fact that they're not I/O bound anymore, and they see that they're more and more compute bound, and it's worth it for them to go into the C++ engine. But they cannot do this for the whole query. So there are parts of the queries in PySpark which they convert to Photon and back to PySpark, which also comes with overhead, right? Conversion from one to the other is not free. So I think on a single node, Polars would always be faster than PySpark, but that's because of design decision, and the caching is different, yeah.
Okay, a few questions. What are the steps needed to make Polars a distributed engine?
The foundation, that was the, we need to get the IRs right, and then if we do that properly, the rest rolls out of it. Of course, we need to be able to spin up machines and to communicate that, but that's not, that's more an engineering task. This is the harder problem in translating the Polars DSL API to the lower level representations and making all parts of the Polars API work.
Great. We still have 5 minutes, so those questions keep on coming. So great. Yeah. You have questions. Do you have any plans to add a visualizer to the Jupyter environment to do things like monitoring operations across threads, similar to the desk scheduler?
It's not that centralized, I would say. It's harder. You can actually run multiple Polars queries on the same thread pool. I think if you design something for distributed, you will have this more centralized, and the contention of this decentralization isn't that costly. But I think on a single node, it's more costly to communicate this stuff, I think, especially in how fast we want to execute queries. So I don't think we will do this for this single node. I think for a distributed engine we will, and it will also fall out of the hardware because we will have a centralized task queue, a centralized, you will need to know if your runners are still alive, which you don't need to know on a single node because the OS handles a lot of stuff for you. So we also we can lean on the OS there.
I know we have a person from the audience raising a hand. Could you please come to the stage because we have to record the question? Okay, yeah.
When we talked about superstrings, I failed to understand the disadvantages of using the Umbra representation. So what's the price you're paying for using that representation?
So the question is, what's the price you pay for going from the old representation to the new one? The price you pay is that the negative side is that you need to do some garbage collection because there can be strings in the buffer that are not alive anymore. The upside is that you have everything in a single tag, and you can, or not everything, but you have got prefixes and length in a single tag, which you can do quick comparisons on. So you have got more optimization performances. But the biggest difference is that a filter or a gather operation, so a gather, if you do a join, you need to gather the results. If you do a group by, you need to gather the results. Any indexing, getting values by index, gathering the other string type costs linear per item for the string length. So you would need to copy the bytes of the string, which can be cheap if the string is small, but if the string is large, it will get pathologically expensive. And this cost can bring your query to a halt. So that's you will get more optimization options. You will get a downside because you need to do garbage collection, but you get an upside because you lose a pathological performance case. And the pathological performance case is so pathological that it really breaks stuff.
Okay. Any final question from the audience? please.
I saw a lot of pandas developers here, and what would you say would be the best way for a pandas developer to learn polars? Just to look at your YouTube videos, or just jump into documentation, or and
Pandas developers as pandas users, or the developers of pandas?
No, I mean users of pandas.
Okay.
And also congrats on your deal with NVIDIA.
Yeah, thank you. Yeah, I would say if you want to learn polars, there are some bad habits you need to unlearn if you're a pandas user. If you write polars and it looks like pandas, you're doing it wrong. I'm serious. Please read our expression guide and understand the gist of expressions and context. If you have that, if you understand that truly, the rest of polars is extrapolating knowledge, because it will flow out of that. And we accept expressions in any operation, in filters, in group bys, in aggregations, in join keys. So if you understand the expressions, you can do anything. So read the expression guide and start tinkering. Yeah.
Any last thought we would like to share? Okay, great. So big warm applause to Ritchie for this great speech.
Thank you.